Hello, we are
Team BASKeTS.
This project is sponsored and inspired by the friendship of Dr. Whit Smith of the School of ECE and Dr. Okir Frempong, the medical superintendent at Lekma Polyclinic in Accra, Ghana, who met at church.
During dinner I said, "So, is there anything you need?" Thinking maybe he wanted groceries or something.
But what Dr. Frempong really needed was essential medical equipment for his hospital.
They said, "No, we want to build an incubator."
So we decided to make an incubator. Ghana has a 6 times higher neonatal mortality rate than the US, with 34 in every 1,000 live births resulting in death of the child. This is largely a result of the lack of availability of working incubators in the country. Current inexpensive and easy to repair incubators in Ghana, like the Draeger Isolette, can still cost upwards of $2,000 and contain complicated electronics and parts that often have to be imported to be replaced. The strain on funds and labor placed on the hospitals in the country as a result does not allow for proper care of premature neonates. Our group's objective is to create an indigenous fabricated, low-cost, and locally maintainable neonatal incubator.
The main design goals for our project are influenced by the location and users of our product. These goals include being easily fabricated using affordable parts found in Ghana, well documented for debugging with limited knowledge of electronics and tools, able to provide a safe environment for the baby and clinicians, and resilient to the frequent power outages in Ghana. One issue that was very important to keep in mind while making structural decisions was the type of material used in construction. Because of its availability, cost, appearance, and structural integrity, we decided to make the majority of our incubator out of acrylic. One of the challenges faced by users of commercial incubators in Ghana is complicated and expensive electronics that are not easily fixed or replaced. For these reasons, we are making sure to write thorough documentation involving assembly, troubleshooting, and operation of the incubator. Another important aspect is the ability of the clinicians to perform operations on the baby while it is in the incubator. This helped us determine the size, door, and hole placement and shape of the enclosure. Additionally, we added curved edges to the enclosure to keep the operator safe. And finally, because power outages are frequent in Ghana, there must be a fail-safe option in case the DC power from the outlet is not available. This is why the incubator was designed to be operable on a car battery as well as a backup in case the power goes out.
The final design has 4 layers. The top layer has the bed for the infant on top of a grate that allows airflow from only the head and foot directions. The walls of this layer have several access doors to allow clinicians to care for the baby inside. The doors are placed symmetrically to allow for equal access to both left and right-handed clinicians. It also has 2 grommets to allow sensor wires to run out of the enclosure. The walls are puzzle fit together for an easy assembly without tools. Acrylic glue is then applied between the tabs to bond the walls together securely. This process results in a sturdy enclosure without sharp edges from screws and bolts. The next layer is the ventilation level, where the automotive blower intakes air to circulate. The air flows through the top of the blower and out from the sides, so the separating layers to keep the blower from circulating the same air. There are also vents that can be opened to allow fresh air from outside the incubator into the enclosure. The layer below is the heating layer. This is where the air flows out of the blower and past the heated resistor plates that warm the air through convection. We performed several heating tests throughout the semester to ensure that this heating method is effective and is able to get the enclosure to a suitable set point temperature and keep it there for extended periods. The system reliably reaches the set point temperature within 32 minutes, which fulfills our time to heat specification. Further analysis of the heating test results allowed us to determine the distribution of air. As expected, the bottom is hotter than the top because of the resistor plate location. We have run the incubator for 6 hours, and it reliably maintained its set point temperature without deviating enough to trigger the alarm.
The bottom layer is the electronics box. It contains a power supply, printed circuit board, fuse box, Raspberry Pi, and grounding aluminum plate. There are a lot of safety mechanisms put in place to keep the incubator autonomous and functioning in these instances. Fuses are placed before each subsystem, and the power supply has a power relay in place in case of failure. Additionally, there is a 40 amp circuit breaker for the car battery. It provides user-friendly displays that are easily comprehensible by any clinician.
The top 3 layers are the ones that need to be cleaned between patients because they come in contact with the air that the baby breathes. The bed is removable. The layer under the bed is also removable with a convenient handle to allow for easy cleaning and access. These pieces can easily be wiped down with bleach and then water to be cleaned before the next patient. Below the bed is the ventilation layer. This layer can also be removed for cleaning. The next step is to remove the top of the automotive blower and the top of the resistor plates, and then can be cleaned separately. Once all the layers are cleaned, they can be reassembled inside the enclosure and the incubator is cleaned for the next use.
Although the incubator itself is the main deliverable, one of the main goals is for it to be assembled, operated, and repaired in Ghana. We decided to create a user manual, an assembly manual, and a troubleshooting manual. The user manual includes instructions and details on the functionality of the incubator, the controls, startup, and first-time use. The assembly manual details the parts and tools needed to manufacture the incubator and includes step-by-step instructions on how the parts fit together. The troubleshooting manual covers any electrical issues that could be faced while operating the incubator. We wanted to combat Ghana's high infant mortality rate by creating a low-cost incubator that would hopefully help medical staff in Ghana care for premature neonates. Through several iterations of electronics testing and structural redesigning, the BASKeTS team has created an incubator that has proven to be effective and efficient, and we are proud to deliver it to our client at the end of this semester. We hope that our presentation has warmed your hearts.
Thank you!